Swayam Prabha. Digital India. Educated India.
We have 3 more topics left, and one of them we need to complete up. This is the carbon dioxide EOR projects. We'll investigate the, how do we assess and so on. And then we'll look at how effective is CO2 EOR in emissions reduction, because that's really what we're talking about. We're really looking at CO2 EOR to say, do we get tax credits? Do we get benefit from EOR projects? Once we've gone through that, then we'll look at supply chain. And I apologize, I am not much of a supply chain person. So I have, but we are running into those problems with the project that we are managing. So we'll discuss some of those things, also specifically in the context of the large scale CCS project that we have launched. Where do we stand? What are the challenges with in respect to that? That's something I can talk about. And then what are the various supply chain problems? We'll also look briefly at pipelines. What type of pipelines exist? This is the US case. I do not know what it is here in India. I think a lot of transport happens by road, but not most part, for sure. Road transport, rail transport is not going to be practical if you're doing large-scale CCS projects. So we will talk a little bit more about high-density transport of carbon dioxide in a safe manner. And I'll show you some results on solid natural gas projects where we are now continuing that with carbon dioxide. This is in the form of gas hydrates. And then tomorrow we'll complete the solid natural gas and solid carbon dioxide transport, and we'll discuss policy. Okay, so that's what remains in front of us. Okay, so we were discussing CO2 EOR. When we are using carbon dioxide to get enhanced oil recovery. And we closed the day yesterday with looking at a life cycle of primary, secondary, tertiary oil production. This is a very typical oil field operation. You drill a well, you put the well on production. It drives, the internal pressure drives production for the most part. When that starts to decline, you go into secondary production. The secondary recovery is using water as a flooding mechanism and enhancing recovery that way. Once you've exhausted that part, this is just a pressure buildup. Once you've exhausted that part, you go into what's called a tertiary recovery, and there you're modifying the mobility of your oil using carbon dioxide. The carbon dioxide acts not just as a pressure agent. Usually that's not what we're using it for. We're using it as a solvent to dissolve in the oil and reduce the viscosity, and with that sweep up all of the remaining oil. So that's really what we're talking about. And in the scheme of things, this is carbon dioxide injection. Here is sustained recovery of oil and gas. And there are many such projects that are underway. And we'll examine some of them by way of modeling them to see where is bypassed oil, what have we done, where is the gas residing, and what are the emissions control? How much are we reducing emissions in doing this process? We use geophysics. I am a geophysicist, so for me, geophysics is the center of the world. But we build a geomodel. This is a typical geomodel, right? We have various channels and reefs and barrier cones and so on. And we get this from a well log where we drill a well, we get geology information, and from seismic that gives us a large scale structure. So if you look at this geomodel, that is 1,000 meters by 1,000 meters, 1 kilometer by 1 kilometer, depth 100 meters. We take all of this and we populate it with information. Information such as porosity, permeability, fractures, barriers to flow, contrast and permeability. Once we have that, we do a reservoir simulation. We do a simple flow model and we say we are injecting, for example, here in the central location, and we look at how far does this gas saturation go, and that we have a barrier over here that's marked by blue, and that gives us a limit to the carbon dioxide in that place, and it's transporting out primarily over here. So we take these reservoir simulation models and we forward model what the seismic response should be, compare it with what we get, and do what is called a history matching. Okay. So here's a example of EOR field. This is in Montana. It was produced in separate different blocks, time wise going from 1, 2, 3 and so on. We had a data set from this location here. And so we were checking what can we match our reservoir simulation with the seismic. This is what the input data looks like. This is a 4D seismic amplitude map. Quick question, what is 4D? Yes, 4 dimensions. The 3 dimensions, time, right? So we have 3 dimensions, X, Y and Z, and the 4th dimension is time. So when I say this is a 4-dimension map, that means I have X and Y here. I have taken one time slice and I have looked at the time. I have taken one depth slice and I've taken the time difference from time A to time B. And so that's what we're looking at. This is the well log information from the same area. We had multiple episodes of logging, and so we could do before and after. This whole thing had a central injector, corner producers. So that's what the constellation looked like. In all of this, we are really trying to determine where does the fluid reside. If it's here, this is carbon dioxide, that's water, is it pushing things away, and how much is there? And so we went in and said, okay, let's have a geomodel. This is what our geomodel looks like. This is the same seismic attribute map, the seismic attribute being an amplitude. The gray on the top is the top seal, gray on the bottom is the bottom seal. Porosity variations are given here between 20 and 50%. 50% I would not believe, that's way too much. So the main porosities were around 20 to 25%. That's what we're looking at. This is inferred porosity from seismic. So this is a changed porosity. So what we do here is we take all of this and we calibrate the seismic signal for change in signal amplitude, the signal attributes, seismic signal attributes. Attributes means just quality. This can be the travel time, it can be velocity, it can be the frequency content, it can be the attenuation, and a host of other parameters. So the part that we look at is, here is the reservoir part, this is the bottom seal, this is the top seal, and you put everything together, plug it up with all sorts of electrodes. In this case, there are velocity sensors for compressional shear velocity. There are electrical conductivity sensors here to measure the saturation. There are pore fluids inlets and outlets to measure pore pressures. And there are strain measurements that are not shown here, but there are strain measurements on all of these, and there are temperature sensors on every one of them. You put all of that at reservoir condition and you do the measurement. So then you do the calibration of, for example, your seismic signal and say, how much of an amplitude difference should I expect from which saturation? That becomes my calibration. So I take that calibration data and I invert field data into a saturation. Okay. So that's the step. In that, we also try and say, what should we expect to see happening? So this is work done by a postdoc of mine, Matthias Pohl, and he went in and he got the oil from the oil field and said, let me mix it with carbon dioxide and measure what happens. This is low field NMR, so it's not a compositional NMR, but it's just telling us the mobility of the hydrogen. Okay. This is the oil here with 50 psi of carbon dioxide. Carbon dioxide is in gaseous state. You increase the pressure of carbon dioxide to 500 psi, all we see is this peak going over to longer relaxation times, which tells me that the viscosity of the oil is reducing because carbon dioxide is dissolving in the oil. As soon as we change to liquid state at 1700 psi, we see a separation. We see that there is a shorter relaxing fluid and a longer relaxing fluid. That tells me that my oil has segregated into a lighter fraction and a heavier fraction. And this is only with carbon dioxide in the oil. Now we said, okay, that's very nice, but there could be brine. We could have brine in this, and that's what is separating out. How do we know what this is? We opened up the pressure vessel and we found that indeed there was no water present. This was primarily lighter fluids that we could see. We went one step further and we said, well, let's look at the viscosity. So we see that you can match the viscosity with the changes that are happening. This is 50 psi, that's somewhere here. 500 psi is out here. 1700 psi is much further out. So what we're looking at is a viscosity decrease just with gas, and then when we turn into liquid phase, the viscosity reduces substantially. If we are in liquid state, we also get a separation and segregation of the fluids, and you get two separate peaks. No, this is in a pressure vessel in the laboratory. But we'll look at reservoir simulations for the reservoirs, for the in situ fluid as well. So we had this sort of information, and then we said, but we have also water in it. It's not just a two-phase fluid, not just carbon dioxide and oil, but we also have brine. It's always present. So we added brine. So we said, okay, we can mix these three up. We had oil, brine, and then we started dosing it with carbon dioxide. Out here, we have 50s, 250, 750 psi. We see that there is a slight shift, but really nothing to write home about. Sorry? I do not know. We mixed it according to the oil field properties. So we had exactly the composition of the brine and we mixed it that way and then we put it in. I don't remember now. This is work we did, I think 7-8 years ago. Yeah, 21. So 7-8. Seems like 7-8 years ago, but it was a few years ago. So I don't remember exactly how much brine, but it was enough to give us a signature. And this we thought was the brine signature. And it started changing a little bit, but when we increased pressure, we saw here, for example, there is the viscosity decrease that we expected. As we started adding carbon dioxide to the brine, that acts as an impurity, so that changed the peak somewhat, reduced the hydrogen index of the fluid. When we went into liquid state, this curve for 750 is repeated over here. At liquid state, we suddenly saw a very large increase in where we thought it would be brine. And we saw a viscosity increase in the heavier fractions. So in this case, the peak is moving slightly towards longer times. In here, it's moving towards shorter times. So two separate phenomena. In one case, we are adding lighter hydrocarbons to this mix here. So this comes in and has a relaxation peak around the same time as brine, free fluid. As we remove these hydrocarbons, the lighter hydrocarbons from the oil, the residual oil becomes more viscous. As it becomes more viscous, we go towards shorter relaxation times. And so this was a very interesting phenomenon. And we said, okay, can we see this in the oil field? So we took the properties here of the oil, the composition, and we created a geomodel. We gave it the properties from the reservoir. We said we have a shale, that is a no-flow zone. We have a siltstone below that is much lower in permeability and porosity. And we have the oil-bearing zone, that is a sandstone, and it has much higher porosity, much higher permeability. Right? So this is our main flow zone. There will be some leakage into here. Here we have set this as a no-flow zone by giving it a very low permeability, what was measured. And so we take that and we start reservoir simulations. This is what we get here. We have a central producer here and we have 4 injectors. Now, since then we have learned how to do it better, and we know that this shape is not real. It is more gradual. The shape is still there, but it's not as dramatic as what we are modeling here. But what you should take away from this is these are C6, C15, C20, C36. These are going from lighter to heavier fractions. Out here, we're looking at normalized saturation of each one of these fractions. So at the injector site, we have driven out all of the lighter hydrocarbons and we've pushed them through to the producer site. Is this the carbon levels, the C1, C2, C3, methane, ethane, and so on. So this is the oil composition. Yes. No, this is an UR field. This is not. Yes. Yeah. But you would expect to see the same thing in a depleted field, even more dramatically, because now you're starting to produce and mobilize oil where you didn't want to mobilize. So that's a big challenge here for depleted reservoirs. And so once we had that, we started looking at this full picture, because normally if you take only the saturation, you do not see much of a change, because saturations change as per what carbon dioxide is there. We're not looking at the composition of the oil, but the composition of the oil is changing based on what is being preferentially produced and what's being enriched and left behind. And so what we see is we are leaving behind all of these heavier hydrocarbons. Now, we talked to the reservoir simulators and they said, yeah, we know this. I said, well, why didn't you tell us? And said, you didn't ask. As a seismic person, I go to them and tell them, okay, you're doing your reservoir simulation, give me a saturation map. They give me a saturation map. I model that and I say, it doesn't match my 4D seismic, there is a problem. But if I ask them, give me the composition, they give me exactly this picture. They not only give me this picture, they also give me the fluid modulus, which I can compare with my calculated modulus. And so this is exactly what Simi did. Simi was a master's student in my group, and she went in and said, okay, I have this simulation result. Now let me calculate what the seismic response will be. And so she went in and took this part here and created a model and started looking at the changes in fluid modulus, in the fluid velocity, and in our reservoir modeling for geophysical response. One of the things which was very clear was there is a geophysical implication of enriching certain areas in heavier hydrocarbons because they are viscous. If they're viscous, then they behave more as damping agents for seismic waves. And so we get not only a velocity change, but we get a frequency change. In the seismic world, that's a big thing. And so a viscosity change we can map very nicely. And if we are modeling a viscosity change, we went in and said, okay, let's model then the response, the geophysical response of that viscosity change. And so we looked at the current status of models and we said, we should change the models and create a better model. And that's what we came up with, to say, if this is my measured response, this is what we measure. Here's the central producer. These are the 4 injectors. Now, if we take the change just in the composition and the saturation, here's the saturation profile. This is the density profile. Here's the impedance profile, and this is the viscosity profile. And so we are able to much better map this sort of a change that we were not able to do by doing just simple saturation models. And that made it a very, very important consideration to make when we are looking at EOR models. And we went in from there and did all of the models and compared before and after, compared with the old way of doing this and with the new way of doing this. And so, and there were a series of suggestions and recommendations on how to move forward. We have looked at the Sleipner project before. This is the one in North Sea, where there is injection in the Utsira sand. This is the top sand, and this is the base of the sand. Here is where the injection is happening. C marks the injection point, and we see a gas chimney where the injection is, and over time that sort of dissipates and spreads out. So you can map that in seismic, and then the interesting thing now becomes to model it using a better density response from reservoir simulation as well as a saturation response. Again, the challenge that we had in this was to see whether this response maps the volume of injected carbon dioxide. And that part, they are able to come in. There was a latest paper in 2022, 21 from colleagues at NTNU, Norwegian Technical University in Trondheim, and they were able to map the saturations with history matching. History matching in an oil field terminology means you have injected volumes over the period of the injection, and you're matching that history with your seismic history, with your 4D maps, and you're going back and revising and saying, here's how the model should be tweaked. So you match the historical injection levels with the historical seismic amplitudes. And then we can take all of that and put that in a simulation, and we can model various effects. We can model the change in amplitude out here. We can model the change in velocity, depending on the type of saturation we have. If we have a dispersion, we can model the dispersion on various types of loss models, and we can model cementation and dissolution. So there is a very big toolbox of relating the texture effects, the alteration effects on velocities and on seismic signatures. One thing which we are still struggling with, as I said, was to map saturation. Right. Yes, you can map that with the seismic as well. In this case, in the case of the EOR, not yet, because it's a dynamic case and we're moving carbon dioxide and we're producing. So you don't have enough time to get the segregation. What we did not see in this thing was, we did see a variation like this. We did see a little bit of a segregation, but that was not, it was transient because it went away as you started. And they were, in this case, they were injecting carbon dioxide followed by water plugs, carbon dioxide, water, carbon dioxide, water. So that mixed up the whole segregation part. Over time, you would expect to see that. Right now, this is all a dynamic state in Sleipner as well as in Bell Creek. Just to make it flow better, to make it push out the pressure and keep, prevent it from, yes, from backflow, and to have compartmentalized. So you wash it with water and then you put in another slug. So it gives you better production because you're pumping it. So you get a pump of carbon dioxide with a pump of water, carbon dioxide, water. It gives for better flow and better production. Okay, so we also went in and said, okay, we have a problem with the machine, with the saturation models. So we took a very typical saturation model and we went in and said, let's look at machine learning. Can we make a better model using all of the strength that is promoted from machine learning? And here what we did was, we said, okay, instead of using machine learning as a predictive tool, let's look at it as a error mapping tool. And so first we went in and said, okay, we can use hundreds of images and we can say, I want to classify a cat, right? This is the image of a cat. And we have we create a model and we say, is this a cat? Is it not a cat? And what that does is it comes back and says, yes, this is a cat. No, it's not a cat. And it is more of a black box. Behind the scene, it has an explanatory web interface, and that says, what are the describing features? It learns describing features of a cat using the hundreds of training images we give it. And so if I have a cat, images that are very well defined, very well behaved, then it comes back and says, well, a cat needs to have fur, it needs to have whiskers, and it needs to have this sort of a feature. Those are my describing features. That's what the machine learning does. And so you go in and you put in your picture of a dog and it says, no, it's not a cat. You put in a picture of a tiger and it says, yes, it's a cat. Beautiful cat, right? Has the features. It has the shape of the ear that way, and it has the fur, it has whiskers, it is a cat, right? So there have been very interesting examples where they were using this in medicine and they were defining and describing certain phenomena, cancerous tissue. And they had enough images of cancerous tissue till they realized one of the features that was being used to determine whether it was cancerous tissue or not was a scale, because they always had a scale to map the picture. And so that ruler to map dimensions became part of the model to be used as a determining feature for cancerous tissue. So it becomes a problem. If you don't know what you're doing, if you don't know what the black box is, then you can get challenging results from machine learning. So we said we don't want to go that way. We don't want to have a predictive model. We want to build the model for errors. And so we used what is called SHAP values. SHAP is the person who invented this thing. And what that does is you create a model, you have your data, and looks at the misfit, and it looks at the misfit together with the variability of your input parameters. And so that's what we did. And we said, okay, these are the different input parameters for my saturation model. And so I need to have the mineral modulus tied down very, very well. Otherwise, I have high error, right? So this arrow here gives you importance, high importance to low importance. And out here is the feature value, high to low. And this is the SHAP value. And so we went in and said, if we don't know what we are doing, then you can use the SHAP values for any particular model that you're doing to say when should you use it and when should you not use it. And that made it a much more powerful tool than any machine learning predictive models that we built. We built many predictive models. We could not match the saturation as well with the machine learning model, and we tested them against physical models. The physical models performed just as well, sometimes better, sometimes worse. But there was nothing particularly better about them. And so this was one of the ways that we are using machine learning to say when should we not do something, right? Okay, so any questions till now? No? Okay, we'll change tracks a little bit and we'll look at two CO2 EOR projects, and we'll assess them for their emissions reduction. This is what we are requiring to do, or we are oil operators, CO2 EOR operators are coming back and saying, we qualify for tax credits, we qualify as good people because we are controlling emissions by using carbon dioxide as an EOR process, and that carbon dioxide stays in place. And so this is a good benefit that we are providing. Okay. This is the work done by Maureen James. She has since graduated, and she decided she wanted to continue on looking at diffusion coefficients and shale seal leakages in shales. But this part of the work was one fourth of her master's work. So she said, okay, we can take CCS and we can look at the U part, the utilization, which is the oil recovery, enhanced oil recovery, and let's assess how much more oil do we produce, what are the emissions that we generate in producing that oil, and where does the oil get used, how much emissions are generated from that excess oil. Let's do an entire budget of it, right? So these are the climate goals and these are the projects that are planned. There are currently 30 projects in place with an annual capacity of 42.5 million tons. Okay, this is million tons per annum. So 30 projects that are each putting in 1 million tons per year. There are 11 under construction and there are 153 projects planned. So all told, we are nowhere close to the 10 gigatons of carbon dioxide that we need to remove by year 2050. And so the calculation comes in, well, let's count in also the CO2 EOR projects. Do we get more capacity that way? We've looked at this a lot, the CO2 EOR life cycle. We have a supply of carbon dioxide. There is a DAC hub here, McElmo dome, whatever the supply might be. This is the captured part. This is geologic carbon dioxide. CO2 EOR projects use any one of these or both of them. That gets put into a refining plant separations, compression, gets transport, the transport, whichever way might be, gets emissions, it's put into the oil field and injected in the subsurface. As it injects, you produce oil. That excess oil production gives us carbon dioxide, goes to the refinery, gives us carbon dioxide, and gets used, that gives us carbon dioxide. So we track all of this, right? We track how much excess oil have we produced and what is the emissions that we have generated for that process and how much have we gotten rid of in this process here. So that's the calculation that's happening. As an example, there is a Weyburn field that's been running since the last 30 years. It's been producing a very prolific field. The field is in Canada. The gas is being supplied, carbon dioxide is being supplied from US in Beulah. That's a gasification plant, and that supplies the carbon dioxide. All of that goes in via pipeline and produces oil. It has produced about 60 million barrels of oil, stock tank barrel of oil. Okay. So we have emissions reduction with goals that are low technology, state of the art, risk mitigation, and so on. The assumption is that we will store 2.6 billion tons of carbon dioxide, right? So that's the scenario that is being promoted by the DOE, US Department of Energy, using EOR. One is business as usual. We keep doing what we are doing. We are having a miscible displacement of oil using carbon dioxide, and that gives us enough volume of about injection volume of about 0.4, 40% of hydrocarbon pore volume, right? And we can inject more where we have a much better target, much better operations, and we can recycle and manage carbon dioxide that way so that we get a much better displacement. The part which is really interesting is the supply. What they are assuming is the supply is both from natural and anthropogenic sources. Now, natural sources are geologically occurring carbon dioxide. This is emissions that were not there, were never going to be there, and are being put out because we are producing excess carbon dioxide. So that's adding to the net emissions. If we are using anthropogenic carbon dioxide, that means we've captured it from somewhere. If we've captured it from somewhere and we store part of it in the subsurface, then we have a net reduction, and it can offset the net emissions increase from using excess carbon dioxide. There are a number of natural sources in the US. There's a Bravo field, McElmo, Sheep Mountain. All of these have large amounts of natural carbon dioxide that is being tapped. And so it became a very interesting thing. These are the conversion factors. We compared two basins, the Permian Basin, which is, according to the Department of Energy, a more modern operation, and the Weyburn field, which has been in operation since 30 plus years. Okay? And the conversion we're using is that a barrel of oil, when it's consumed, regardless of how it's consumed, generates about 0.5 metric ton of carbon dioxide. And we use that information. It can be more, it can be less, depending on the use. It can be also, what we are not looking at is the ease of capture. Some carbon dioxide is easier to capture if it's at the refinery. If it's in a car and you're using it to drive around, that's a distributed source of carbon dioxide, not as easy to capture. We're not looking at that. We're just looking at the volume of the emissions. And what we are then doing is we're saying we take the amount of carbon dioxide that is produced, we add the emissions, we add the amount of carbon dioxide recycled, we subtract from it the injected carbon dioxide, and that gives us the residual emissions that we have. So we take all of that and we compare numbers. This is the Permian Basin. We have about 30 years of Permian Basin. Okay. So what you get is the oil production. Initially there is no oil production because it needs to get into the carbon dioxide, build up the pressure. You have a lot of carbon dioxide that you purchase. You don't recycle any of it because you're filling up your reservoir, and so everything that you purchase is injected. So you have removed a net of 41 million tons of carbon dioxide in year 1. In year 2, it reduces slightly because you start producing oil. You have here 91 million barrels of oil produced as a result of that injection. And so that gives us a fair amount of production emissions. We have nothing recycled yet. We put all of the carbon dioxide that we have back injected. So the net residual emissions is this number minus the production's emission, right? So we go through and go year by year and calculate out what net production we get. So if carbon dioxide is captured and re-injected, we get a net positive emissions of 780 million tons for the oil that was produced, for the excess oil that was produced with CO2 EOR. Right? So it's not net zero, it does produce. But if we were to do it without carbon dioxide, without recycling carbon dioxide, getting it from emissions and putting it inside, that would have been about 1390, almost more, a little less than a double the amount. So that's really what we're looking at. The carbon dioxide from CO2 EOR projects is low carbon, it is not zero carbon. The same thing happens at the Weyburn project. We don't have as much data as we do for the others, but we have a project lifetime of 15 years. We have recovered 130 million tons of stock tank barrels of carbon dioxide and about 20 million metric tons purchased. Now, in this case, in the Weyburn case, they're injecting captured carbon dioxide, which means that is a net reduction of 20 million metric tons for the purchased amount, and there is 3 million metric tons stored. So we can take all of that and create these sort of models and say what happens during the life of a reservoir. We have a million tons of carbon dioxide. We have oil production out here. We have carbon dioxide that's injected. There's a ramp up here, and then for the first 5 years, and then it stays constant, and then when it starts to decrease, you release all the carbon dioxide or you don't inject anymore, and so you get a reduction in the injected carbon dioxide. You can compare all of that. The oil production emissions are in blue over here. So you have this one here, and these go down because the production is going down. And you can take the difference between them. This is the residual carbon dioxide that is left over from the additional production of carbon dioxide, right? So this is, you can take the area under the curve and you get the total amount of carbon dioxide that you have sequestered in the EOR process and the excess amount that you have produced. So there is a net benefit, but it's not a solution, right? It's a step in the right direction. It is a way to finance to get better CCS projects. It is not getting us to reducing carbon dioxide to the levels we would need to reduce, because this is still net positive emissions. It is not net zero and it is not net negative, right? But if it gets us to develop technology that will work better, good. Most of the times we are not developing better technology. We are not developing better technology for storage. We are developing better technology to produce more. So it comes from the, so you count up how much additional oil you make, right? And you take that and convert that into emissions. And then you take how much of carbon dioxide are you injecting? How much are you producing, because you get it recycled. So the difference between the two is what you're storing. Yes, but that keeps going. But you don't, let's say if you inject 10 million tons of carbon dioxide this year, you get back 7. The 3 is what we are saying is stored. 7 comes to the separator, and then you will inject back. Next time you do it, you will get only 3, you will get 4 million tons back, 3 is again stored. So, and if you want to go year after year to store, to inject always 10 million metric tons, then every year you buy 3 million metric tons, that's your reduction, right? Whatever is used up is stored in the subsurface that you're buying, that's you're pulling from either a refinery or whatever capture facility you have. So this is taking into account that recycling effect. You count up everything. Yes, year after year, you don't sequester the same amount because you fill up the reservoir first, right? Once you fill it up, then there is not much capacity left to sequester more, because you are really trying to maximize your return. Carbon dioxide to buy costs money, costs a lot of money. And so companies don't really want to buy. It's a loss for them. This storage is really a loss for an oil company. They don't want to have to buy carbon dioxide. So they're trying to maximize. But year after year, yes, you keep sequestering some amounts depending on the capacity of your reservoir.